Hi, my name is Conor. Welcome to our talk on our paper entitled Multi-Objective Distributional Value Iteration. In this paper, we consider multi-objective decision-making scenarios where the utility of a user is derived from a single execution of a policy. In such settings, a user may only have one opportunity to execute a policy, and therefore they must have knowledge of each of the potential outcomes a policy may have. In this case, the expected scalarized returns criterion should be optimized. Under the ESR criterion, when the utility function of a user is unknown, a set of optimal return distributions must be computed. To do this, we can utilize Esr Dominance, which can be used to compute a set of optimal return distributions known as the ESR set. To do this in sequential multi-objective decision-making scenarios, we've defined a new multi-objective algorithm known as multi-objective distributional value iteration, or MODVI. And MODVI computes a set of optimal return distributions known as the ESR set, and it's important to note MODVI is the first algorithm to compute the ESR set in sequential decision-making scenarios. Just to give some background, we'll discuss multi-objective decision-making, the ESR criterion, and ESR dominance, which can then be used to compute the ESR set. Multi-objective decision-making problems consider problems with multiple objectives. We consider a multi-objective Markov decision process with a state and action space, transition function, and reward function, where the reward function is an n-dimensional vector with n equal to the number of objectives. Modem methods can be single policy or multi-policy. In this particular paper, we consider multi-policy methods where a set of optimal policies must be returned to the user given their utility function is unknown. And it's important to note that the utility function of a user represents the user's preferences over the objectives of the problem. Generally, in multi-objective decision-making literature, two optimality criteria are discussed. We have the scalarized expected returns and the expected scalarized returns. And we're primarily going to focus on the expected scalarized returns criterion. But first, let's just briefly outline the scalarized expected returns criterion. It's the most commonly used optimality criterion in multi-objective decision-making literature, where for the ESR criterion, the utility of a user is derived from multiple executions of a policy. And to compute it, the expectation of the expected value vector is computed first, and then the utility function can be applied. The other optimality criterion that's generally discussed is the expected scalarized returns criterion, which has largely been ignored by the modem community. In this case, the utility of a user is derived from the single execution of a policy, and to compute it, the utility function is applied to the return vector first, and then the expected utility is calculated. So generally in the modem literature, when the utility function of a user is unknown, a set of optimal solutions is computed and returned to the user. So generally, Pareto dominance can be used here in the SCR case, and using Pareto dominance, then the Pareto front is returned to the user. However, this isn't really applicable for the ESR criterion, so a new solution concept was defined by Hayes et al., known as ESR dominance. And that ESR dominance can then be used to give a partial order over policies under the ESR criterion. And to compute ESR dominance, a return distribution must be computed. And we can see here kind of the definition of what a return distribution is. A return distribution is represented by Z pi. So to calculate ESR dominance, the cumulative distribution function, or the CDF, of each return distribution must be computed. And once we have the CDFs of each return distribution, we can then utilize the dominance criteria or criterion here in equation 2. And we can see here that Z pi ESR dominates Z pi prime if the following conditions are met. And the resulting set of optimal return distributions then is known as the ESR set, which is defined in equation 3. Just to kind of outline why a distributional approach must be taken when dealing with the ESR criterion when the utility function of a user is unknown, let's just check out lotteries 1 and lotteries 2, and we can see here that both lotteries have 2 returns with different probability. So under the SCR criterion, as I've mentioned already, the expected value vector for each lottery must first be computed. So we can see here we have the expected value vectors of both lotteries. And then we can use Pareto dominance then to determine a partial ordering over these lotteries. So given there are only 2 lotteries here, it's not very clear, but if there were more lotteries, we could start pruning away dominated and keeping non-dominated lotteries and then return those to the user. And once the user's utility function becomes known, they can select the lottery which best reflects their preferences. However, we can't use the expected value vectors under the ESR criterion, given that to compute the ESR criterion, we actually have to apply the utility function first and then calculate the expectation. So immediately we need to move on to new methods, and the best methods that actually can allow us to compute the ESR criterion is a distributional method. So therefore we must take a distributional perspective on decision making when dealing with the ESR criterion when the utility function is unknown. To do this, basically in a sequential decision-making settings, we've come up with a new algorithm called multi-objective distributional value iteration. And basically, MODVI computes the ESR set in sequential decision-making scenarios. Basically, we cannot use a lot of the traditional methods like the Bellman operator for this algorithm, given that we're now dealing with distributions rather than scalars or vectors. So we actually have to replace the Bellman operator with a distributional Bellman operator, which is defined here in equation 4. And we use this then to update the return distribution for each state action pair. But before we get into more details about how the sets are updated and pruned to return the ESR set, we need to discuss how the distributions are represented and what they actually look like. So to represent a distribution in multi-objective settings, MODVI uses a multivariate categorical distribution. That's very similar to the distributions used by Raymond et al. And Belmar et al. Each distribution is parameterized by a number of atoms where the distribution has a dimension per objective. The atoms outline the width of each category and are bounded by the minimum returns and the maximum returns. And both of these values need to be known a priori. And we can just see a brief sketch or brief outline of the distribution here in equation 5. Given MODVI is a planning algorithm, the algorithm has full knowledge of the state space, action space, transition probabilities, and reward function. So therefore, at each iteration of the algorithm, we can, for each state and action, back up a set of optimal return distributions. And we can see how this is done in equation 6. So during the distributional Bellman backup, each return distribution in the set of return distribution Z is updated with the reward R. So basically, to update the distribution, the distribution is shifted relative to the reward. And that's done for each distribution in the set capital Z. Once we have that completed, we then just multiply each distribution in the resulting set by the transition probability. And then finally, we just compute the cross sum for each resulting set of updated return distributions. And that's for each next possible state, S prime. And you can see that how the cross sum is done in equation 7. And just as a note, I would refer you to the full paper where we give a step-by-step example of how each of the steps outlined in equation 6 and equation 7 is calculated. And it's quite intuitive, so I would recommend just taking a look at that if you need more clear details. So we want actually to return a set of optimal return distributions to a user. So currently our sets at the moment are full of basically every return distribution. So what we need to do is actually start pruning out the distributions that are dominated and dominated by in the sense of ESR dominance. So to compute a set of ESR non-dominated policies for each state, we define a new algorithm known as ESR prune, which computes a set of ESR non-dominated policies by removing ESR dominated return distributions from a given set. And that is defined here in equation 8. And I've included the algorithm here for for reference. I'm not going to go into extreme detail here, but we can see that we just basically iterate over the distributions in the set, utilize ESR dominance, and then remove out any distributions that are dominated. And that leaves us then with a new with a set of non-dominated return distributions, Z star, and then by iterating over the multi-objective distributional value iteration algorithm for each state and for each action, and by executing both equations, by doing the cross sum and multiplying by the transition probability and updating the distributions, and then pruning away the dominated distributions. As this iterates over, we eventually backpropagate the optimal set of distributions back to the initial state. And then we can return those distributions to the user, and the user can select an optimal policy which best reflects their preferences once their utility function becomes known. Again, for more detail on the algorithm and how all of this fits together, I would strongly recommend that you just take a look at the full paper. There's a very detailed example, a couple of very detailed examples that kind of give some really good intuition onto how ESR dominance works and how this new multi-objective distributional value iteration algorithm works also. So also in the paper, we've evaluated the algorithm on 3 different problem domains, but I'm going to concentrate on one problem specifically that I think gives some strong intuition about the importance of ESR dominance and the importance of optimality criteria, selecting the correct optimality criteria at decision time, or before computing the actual sets. So basically, the problem that I'm going to introduce is space traders, and space traders was presented at ALA actually 2 years ago by Vamplu et al., and it's a multi-objective benchmark problem with 9 policies and a small number of returns per policy. So it's an intuitive example where we can actually analyze the results and compare the solutions, and it's quite small, so it allows us to kind of relay the important information. Space traders only has 2 time steps, it has 2 non-terminal states, and 3 available actions per state. And the overall goal of space traders is an agent must deliver cargo from its home planet A to some destination planet B, and then return home again. And it must avoid space pirates, basically. And if they'd encounter space pirates, there is a chance that the ship will be destroyed and the mission fails. So basically, we're trying to minimize the time taken to complete the mission, and also ensure that the maximize mission success, basically. Yeah. So first, I want to present the results from each return distribution in the ESR set. And we've plotted these all on one plot, but in reality, if you were to present these to a user, you could present one distribution at a time and have the user scroll through them then. Or you could present them on multiple different plots, but just for space comparisons, we needed to put them on one plot for this. But you can see here, each shape represents an individual return distribution, and the color then of the point on the graph represents the probability of that event occurring. So obviously, as you can see here, I know it's a bit full, but if you had one distribution per plot, you could see the likelihood of each event occurring, and therefore the user then has a full knowledge of the different events that can occur and also the probability of them occurring. So it gives the user a much more overarching view of what actually will happen when a policy is executed, whereas an expectation vector just gives you one point, and it's very difficult to discern if something catastrophic could happen that may not actually be represented in the expected value vector. But when you have the full distribution plotted out, you can obviously see that, oh, something bad might happen here. And even though there's a low probability chance of that happening, I do not want that. So therefore, I'm going to remove that policy from my consideration. So it just gives the user more information at decision time to understand the outcomes that each policy may have. And this is particularly important if you only have one opportunity to execute your policy, which is in line with the ESR criterion. And finally, just I think it's an important slide that highlights the difference between the ESR and the SCR, and basically what the optimal sets actually return to the user. So we have the Pareto front, which is plotted as a blue triangle, and we have the ESR set, which is a red circle. And we plotted the expected value vectors for each policy in each of the sets. And we can see that the Pareto front and the ESR set for space traders are actually quite close. They're very similar, except for one policy seems to differ between the ESR set and the Pareto front. So while this might seem not that significant, initially it is actually quite an interesting result, given that if you were to return the ESR set to a user, an extra policy would be contained, and therefore, if you were to show the user the Pareto front when you should actually be showing them the ESR set, the user is actually missing an extra policy that may actually reflect their preferences better, and therefore, if you were to learn the Pareto front when you should be learning the ESR set, the user may actually select a policy that is suboptimal for their preferences, and therefore kind of highlights the importance of actually selecting the dominance criteria correctly before an algorithm is selected. You must understand what exactly you're actually trying to optimize for. So selecting an SER algorithm when you should be using an ESR algorithm actually could mean that a user ends up selecting a policy that is suboptimal. And obviously, I know there's only a number of policies here, but if you were to, apply this to a real world setting where there are hundreds of, maybe even thousands of policies with different outcomes, and some being, you could severely limit the user's ability to select optimal policies by returning them the wrong set of policies, and that could have very negative outcomes in the real world. So it just highlights the importance of optimality criteria in multi-objective decision making. So just to conclude our talk, we've shown multi-objective distributional value iteration is able to compute a set of optimal return distributions known as the ESR set. We've also shown that the policies on the Pareto front and the ESR set can be different. And we've also highlighted that distributional methods offer insight into each potential outcome a policy may have, which can be very helpful, I think, in multi-objective decision making, especially when the user's preferences are unknown. And I think as a final note, it is very important that the correct optimality criterion is selected. Basically, policies that are optimal under the ESR criterion may not be optimal under the SER criterion. And as I've shown back here, this extra policy is actually Pareto dominated, so it's not optimal under the SER criterion. However, it is optimal in the ESR set. So I think that's just a very important finding. So that's it. That's our talk. If you have any questions, please feel free to reach out to us on the Slack or send us an email. We'll be available and around at ALA for both days. So if you have any questions or just want to talk about anything about multi-objective decision making or the ESR criterion, or you have any ideas or anything like that, it'd be great to chat. So feel free to reach out. And thanks for watching.